Welcome, everyone. And we have our own Krish giving the workshop today. For now, I think I'll hand things right over to Krish and let him get started.
Okay, thanks, Dave. Just wanted to alert you that in the conventional way we do this workshop, it's really about how to rather than what. So I will be talking about PureShift in tabular domain. That's for those who may not be familiar with these new terms. I will take some time in the front end to briefly introduce, because I was reminded by some of my Ivan colleagues that there are attendees who may not know everything about craft or everything about what we mean by tabular domain and so on and so forth. So this is really a paper that Dan and I published recently, but the talk is more going to be the thought process that went in building this, and hopefully that will be of interest to the group rather than the what we published, which is already in public domain. So let me get going. I'm going to defer, not defer actually, I'm going to chew into the time that I might need to talk about Ivan upcoming and all that, because as most of you know, that if I'm given 1 hour, I tend to talk more than that. So I do have about 45 slides to go through. Hopefully within an hour I should complete. And in my tradition, last night I gave a copy to Dan, and then I promised him that no guarantees that will not be an update, and they stuck with that guarantee that I did make a couple of updates this morning. So that's just the way it goes. So let's get going. I'm going to first share my screen. Hold on for a minute, if you can. Okay, share my screen, and then I'm going to put this in full. Okay, so I'm assuming that you can see my PowerPoint. If not, yell. So this is what I'm going to talk about, PureShift in tabular domain via a new appended acronym called CRAFTps. So let's first take the 3 phrases. PureShift. What do we talk about PureShift? It's essentially a broadband homonuclear J decoupling. This has been championed by several groups, primarily the Manchester group. This is an spectrum probably 15 years old or something, from Varian FID library, strychnine spectrum. You can see that this is a strychnine spectrum, and the chemical shift spectrum is what we get. And if this is an azithromycin spectrum, that's a quinine spectrum in a benchtop. I want to leave this particular spectrum on the screen is to show that J coupling is more often, particularly in the low field, is more often an annoying feature than useful. Most of the time, the field itself is small, so that means almost all couplings are significantly strong and second order. And so really deriving coupling constants from that requires a significant amount of effort. Whereas, so why not get rid of them? That's the idea. So benchtop on the very top, the PureShift spectrum looks pretty good to me, and that is significantly useful, more useful than the spectrum on the bottom. I can't even get a chemical shift out of the spectrum here, let alone J value. So get rid of the J value when we don't need it. That's the idea in any PureShift type of experiment or process. So what does that, I want to talk in terms of what does the multiplet mean? So what does PureShift really mean? In time domain, if you have a doublet, so here is 2 doublets. One is on resonance chemical shift. The other one is off resonance chemical shift. The gray line is the chemical shift. So that in a doublet or a multiplet, some spins, some transitions are precessing, lagging behind the chemical shift. and some precision, some vector precisions of the multiplets are running forward, running faster than the chemical shift. So, but they all follow the chemical shift. They are essentially vectors that are precessing ahead or behind their respective chemical shift. So when we acquire a spectrum like that, all we do is we get all frequencies, meaning that these doublets or multiplets or quartets or all show up as an individual peak in your spectrum. So that's your coupled spectrum of this one happens to be strychnine. If I'm sure there are many of you who know strychnine spectrum by heart. That's a strychnine spectrum. So the idea behind broadband homonuclear decoupling is by conventional method, meaning by pulse sequence method, is essentially as the two vectors going back and forth, right in the middle of some time, you invert the spin states of the passive spins. So the color code in this particular case is as a doublet, the color code changes, so they start to spin the opposite direction. That is achieved either using shaped pulses like in the good old bash sequences, or much more fanciful and more powerful way, doing slice selective pulses between chunks of dwell point. It doesn't have to be between dwell point, between chunks of dwell point, PS1D and the very popular Psyche experiments, or part of that, or using isotopic selective pulses like the bird pulses in pure shift HSQC. Essentially, all of this is to make sure that we detect. The idea is we only sample when the multiplet vectors are at or near the chemical shift vector. So when they are further away, we are not sampling the data. Whenever they come together, we sample it. So it's as though we cheat the system, the receiver, to think that all the frequency that it sees is always at the chemical shift position. So when you do the Fourier transform of that, you get a pure shift spectrum. That's the idea behind. Pure shift experiment, essentially averaging out the precessional differences between of the multiplet component, so that they all receiver looks at it and then say they all precess at the same frequency. That's essentially what we are doing here. So I'm going to now shift a little bit gear and then introduce what we mean by tabular domain, because this is one of the phrase that we used in the title. So let's start with time domain. So we pulse. We have, in this particular example, we have 3 spins and 3 magnetization, blue, red, and green. And the amplitude of the magnetization at time equals 0 is the vector magnitude at t equals 0, and the direction is a phase of the 3 magnetization that are there in this example. So as you start to acquire each one, they are all spinning. We just start to turn on the receiver. They continues to spin. So some of them decays faster. The red one decays faster. The blue one is slower, and the green one is intermediate. And we detect the resultant vector all the time. We always detect the resultant vector of all these 3. And then when we do a Fourier transform, we get the spectrum that we all love and covet, and that's exactly what we want. And we are happy about that. But the point that I wanted to bring up here is the decay rate constant, which is the rate at which they decay, is nothing but a rate of change of amplitude. So as long as you follow the amplitude as a function of time, you should be able to find the rate of change of amplitude. And frequency is the rate of change of phase. As long as you follow the phase of the magnetization as a function of time, you can compute or you can derive the frequency. A Fourier transform does that for us. So we get the spectrum where you have the frequency along one axis and the peak height along the other axis, and we are very happy about that. And we can modify how that frequency domain spectrum looks and behaves and make us happier and all that by essentially changing the way we prepare the spin just before the acquisition. And so during the acquisition, this representation reflects what the pulse sequence did. that's the idea. So the idea is the choice of the pulse sequence changes the representation or content of the frequency domain. So now let's take in terms of tabular domain in some ways. Instead of just going straight to the frequency domain, about almost 35 years, 34, 35 years ago, Brett Horst published a series of papers on using Bayesian, essentially saying that FID is, assuming that's the three magnetization we are talking about, that FID is a linear combination of three equations, three exponentially decaying and precessing vectors, and that's what Bayesian does extremely well. I am not a mathematician to even understand what he does other than just use the power of that package. And there is a review article by Ackerman and group in concepts of magnetic resonance as well. But what we say that these equations are is really a table of four parameters, and those four parameters are the amplitude, which is the second column, of frequency, offset, decay rate constant, and phase. So this is what describes those three magnetization that is spinning around, and they go back and forth because I'm pulsing. If you imagine that I'm doing a time average there. So in essence, this tabular domain is a representation, this table is a representation of the FID in the component level, at the component of each one of these magnetization in that FID in a tabular format. And then obviously we can essentially take those magnetization table and simulate your spectrum, and voila, we are happy. That's our domain. I call it a user domain. This is what makes us happy. This is what we interpret. This is what is visual. And so the point being, the immediate question is why? Why would we bother to do this when FT is giving you that same information? Why? Assuming this table is a clear-cut representation of the FID, why do we bother to even go through this tabular domain? The interesting part of this is, just like we can change the content or the representation of the frequency domain by changing the preparation of the FID, meaning changing the pulse sequence, here is an opportunity of perhaps taking that table, and because it's a basic table, just like a spreadsheet, you can sort, combine, filter, search, group, visualize, whatever you want to do with the numbers, but within that, using basic NMR rules. That's all we all trained on, using NMR rules. Can we apply that NMR rule to convert that tabular domain into various representations? So now it gives us two tools or two potential places where we can visualize the data in a different way. So most of my work today, most of my talk today, our workshop, is going to be focused on that. Not how do I get the time to tabular domain, but what do we do with the tabular domain to visualization or frequency domain. So I'm going to focus on that. Most of our work in the past and in recent years as well is in that aspect of tabular domain, not in the decimation component of this workflow. So let's take a look at how do we think about doublets or multiplets? In this case, I took a multiplet. So if I take a multiplet, I slowed down a little bit in the spin, because perhaps think of it, I am in a bench top now. It's spinning slower. And so there is a J vector that I again deliberately slowed it down just for convenience. So there's a doublet on the top, and there are quartets in the bottom, or any multiplet you can think of. The chemical shift is in the vector average of all the vectors that describe that multiplet. So if simply in simple terms, chemical shift vector is a vector sum of all the components that are processing around it. With that, that's not just true at the beginning of the FID, it's true at all time. At all time, if I know the properties of individual component, the vector sum would be the chemical shift property. That's the idea behind that. Because these four properties are orthogonal, there are benefits that we get by working in tabular domain. We'll come to that in a minute. So I'm going to redefine, rather than showing you a picture of a vector spinning around, I'm just defining a multiplet. It's a group of vectors that process together in unison around its chemical shift vector. If it is instead of a simple quartet, if it is an A-B spin system, so it's an asymmetric doublet of a doublet, so be it. It's a four vectors. They have a different magnitude because of the strong coupling, perhaps. And that means they also process a little bit faster than the chemical shift, or slower than the chemical shift, chemical shift plus or chemical shift minus. So, but fundamentally, it is still a group of vectors that process in unison, always in unison, in time. And so, if I have that, why not? I can compute the amplitude of the chemical shift vector if I know the amplitude of all the vectors that contribute to that chemical shift. And same thing is true with phase. That's simply from Pythagorean theorem, extensions of Pythagorean theorem, which is probably predates Pythagoras to Babylonian, from what I hear, Babylonian time. That's not, usually in modern time, that's taught in 8th grade mathematics. Then once I know the amplitude and phase, and we know the amplitude, the frequency is nothing but a rate of change of phase. If I know the phase at every time point of the chemical shift of the multiplet, then I know the chemical shift, phase of the chemical shift at those time points. If I know the amplitude of the vectors or multiplets at every time point, I know I can calculate the amplitude of the chemical shift vector, the elusive chemical shift vector, at those time points. Once I know that, then I can calculate. So rate of change of phase is my frequency, rate of change of amplitude is my decay rate constant. That describes my chemical shift. So I don't want to be going back to the FID. I have a table using Kraft or using Bayesian. I have a table that we just saw that in the first slide of the three vectors, the blue, red, and green vectors, that describes each of those vectors as frequency or offset, amplitude, decay rate constant, phase. So if I take a real sample, in this particular case, actually one of the real Kraft table, the Kraft table has nothing else other than just offset, amplitude, decay rate, phase, and we can sit down and quality of this Kraft table description to the FID and all that. That's not what I want to describe today. That has been discussed in several workshops in the past, so I'm not going to go there. I'm just going to say, if that description happened properly, then this table has enough elements to describe that FID, and so each one of those elements is a vector in that contributed to that FID. So if I have that table, now let's think of, in a hypothetical question, if I can somehow sort the table, into subtables, and each of those subtables now represent a multiplet. How is the question that we are going to answer? But if I can do that, then it is a downhill. If I have that subtable describes a 4-line pattern in chemical shift in NMR terms. That is the 4 component of the vector, of the decaying and processing vector. It's not just a vector, it's decaying, processing, and I think in our scenario that's It goes without saying. So if I have that table, I can compute. I have 4 vectors that I represent. I can compute the magnitude of the chemical shift vector. I can compute the frequency. It's actually even easier than just trying to do it a point at a time, because it says amplitude weighted frequency average, or decay rate constant will be amplitude weighted decay rate constant, or T2 star, and I get what I want about the chemical shift vector of that multiplet, of that subtable. And that's what we call the CRAFTps tool. Essentially, it is just no more and no less than a Pythagorean theorem based upon taking these vectors and adding them together and finding a hypotenuse and say that's the chemical shift vector. So the challenge is in that sorting of the table. Sorting of the table into multiple subtables, then it is downhill. So what do I mean by that in a picture format? So here is a FID here you can see, and there is a spectrum you see. I'm just going to focus upon a doublet of a doublet in that. This is a prednisone, one of the data in the prednisone. If I have a table, I deliberately put this FID behind. I have the table that describes that. If I can hypothetically sort that into this group of multiplets, because I know that it's a well separated from a chemistry point of view, from an NMR guy point of view, I say, that's well resolved. I say, go to the table and find all the frequencies that are within that frequency limit described by the box and generate a subtable. Yeah, it generated a subtable. How is the question that we are going to come down to? Once I get that sorting done, I have this table, subtable, and I can play with that subtable by itself. I can simply say, show me all the models that are in there individually. Here is all models that are individually. Essentially, I can synthesize that vector into a FID, into a single component FID, Fourier transform, I get a spectrum of one of these blue lines. Or I can simply say, okay, add them all together and show me the sum. And here I'm ahead of my talk in the sense that I'm showing you a Fourier transform result without weighting function. This is a Fourier transform with weighting function. And then I'm also showing you FT and WFT kind of results. These are just Fourier transform results of FIDs simulated from this table. Different ways of simulating the same FID. Now, CRAFTps, I went in the wrong direction. CRAFTps is simply a mathematical operation on that subtable. I generate a chemical shift table. And I can take that chemical shift table and treat that as chemical shift model, treat that as a vector. And then say, okay, show me that vector. And in a frequency domain, meaning as a spectrum, there is your spectrum. That's your pure shift spectrum. Again, this is hypothetically speaking. In this particular case, it's easy. It's too easy. So the little challenge that we face in front of us is, how do I sort this completely unsorted CRAFT table, which is a description of the FID? How do I sort that into subtables, each one describing a group of vectors that recess in unison around its chemical shift? That is fundamentally the challenge. I call it a tiny little challenge, but that is sarcastically saying that that's a tiny little challenge. And we want to do this automatically and objectively. No user need to go in and set, this is the frequency that I'm looking for. Whenever we have a challenge like this, I like to take baby steps. I like to work with something that's very simple. For me, strychnine spectrum is well studied by everybody. I can just listen to them and then say, hey, I can use your advice. And there's a strychnine spectrum. That's a well understood strychnine spectrum, well resolved strychnine spectrum. That probably is why, though it has been used for many, many years as an example data, as example spectrum. There it is. I can look at this and then say, even without knowing anything about strychnine, say, all the multiplets are well resolved. Go to my table, do my stuff that I say within each one of those frequency boxes. So I say, here is a box for this region, here is another box, another box, another box. For each one of those boxes, go to my table and sort them out sort it out and give me X number of subtables. If it does that, voila, I can do these models. I can generate, as in the previous slide, I can generate individual models that shows me that I'm confident that that's what this is doing, in the sense that the FT spectrum is very similar to the model spectrum, and then I can add them in as CRAFTps tool and generate a pure spectrum. Except I cheated. I cheated in the sense there are two cheating I did that you probably notice or not notice. One of them is, here is a chloroform, overlapped resonance. There's a chloroform. I said, okay, I don't know how to separate that out. It is buried in there. I don't want to see it. I just simply put two cursors. I will accept that chloroform into that pure shell. I made a judgment call. The second one, which is even more interesting, that I did, which if you are very familiar with Strickland spectrum, you probably would have thought this. I deliberately excluded that. I deliberately excluded that resonance set because there are two overlapping resonances. So the problem is not with whether the signals are, whether we can subdivide the table. The problem is what happens when there is an overlap, which is fundamentally 99% of the time is our problem. Not in strychnine, but 99% of the time, that's a problem in any unknown. We don't even know what is grouped and what is not grouped. So that is a challenge so I'm going to focus on that challenge. So I know I can do this very easily if it is well resolved. What if it's not resolved? So let's take a look at that. There is your that particular peak. This is, I think, H11A and H14, if you are familiar with strychnine structure, and two protons are there, and that's how do we resolve that? So when I look at the CRAFT table, within that region, I have 8 models. I say, okay, I have 8 models. How am I going to resolve the overlap models in the CRAFT table? That's the fundamental question. I stare at that table a little bit longer than if you stare at that table a little bit longer, it's obvious one easy way to sort them out. I simply say, oh, I have 2 groups of models, each one having its own different decay rate constant. Oh, there is a parameter that I can potentially use in this particular case. So I say, okay, I can bring them together. I'm saying sorted by the decay rate constant, sorted by the line width. So group them in models that are around 5 hertz line width and another one around 1.5 hertz line width. And if I group them and I go through my magic of CRAFTps tool, I get 2 pure shift signals. The 2 red lines are pure shift signals of those 2 models. I am still a lazy guy. I don't even want to look at that FIS, that table to decide what it is. So in this particular type of analysis, I would rather spend a lot more time having fun in building a new nice looking spectrum that I can use to direct my table sorting. So I like a spectrum to direct. So I want to be able to put 2 cursors on either side. You can't erase NMR out of me. I say put 2 cursors and show me that go to this table in this frequency region. I don't even want to see the tables. Yeah, it's a huge table. It's waste of my time or waste of my energy. So we said, okay, let's take a plot. There are 2 parameters here that are kinetic. One is the rate of change of phase, another one is rate of change of amplitude. 2 kinetics. So I simply say, okay, plot one against the other. Okay, so I generated a 2D spectrum. Yeah, I'm touching my nose around my neck rather than straight in front of me. Yes, that's okay. I'm sorting it out, so I call it a T2 cozy. So the CRAFT table by itself is a 2-dimensional in frequency. There is by its definition. That's a T2 star cozy. And if I do this, then I say, okay, here is a group. This is no different than if I'm analyzing an HSPC or HMBC, more HMBC. I say all these guys are very close to each other, unresolved. I'm just going to put a box around it. I call it a cross peak. Yeah. So I did that, and I can do the same thing. I can simply take a look at the T2 star cozy spectrum out of the table, and then simply put a box around it, and then say, show me a pure shift. Voila, it gives me that. And then put a box around it. Voila, it gives me the other one. So I am slowly learning to walk. I'm slowly learning to walk from baby step. And this by itself, the T2 cozy by itself is generated excitement in other groups around those who are using craft, and they are taking it has its own uh, applications that are adding to these to this. But I'm not going to go there. So fundamentally, this is, we can always say this is a serendipitous, unique scenario. Don't waste our time. Yes. So, but let's go back. Let's go back and see what is it that we wanted to do. Resolve overlap models in CRAFT table. Here is a way that we were able to do. Take it into a two-dimensional representation and resolve it. We have been doing this for 50 plus years. Whenever we have an overlap resonances, the first thing we turn to is to do a 2D spectrum. A cozy, started off with cozy, and then we say, okay, no, I'm going to do an HSQC, more modern, and then I do all kinds of fancy variations of HSQC, non-uniformly sampled, whatever you do. We rely upon 2D to do this resolution of overlap region in frequency domain. So the question really is, why not use a 2D to resolve the models in a tabular domain? If the models in the tabular domain represents the frequency domain as well as the time domain, it is just an intermediate step. Why not? So resolving overlap models. So if here is a 1D spectrum of cyclosporin, 2D HSQC, I take HSQC again. Remember, I'm still taking baby steps, meaning that I take things that I understand better. HSQC is completely simplest probably form of a 2D spectrum that I can imagine. So I said, that's a nice one because the carbons are, I understand. But I want it to be, eventually want it to be completely agnostic to the 2D. But let's just first take it with HSQC. Here is a 1D spectrum. That's a 2D spectrum. I don't think it requires an NMR spectroscopist to say that the 2Ds are 2D, the signals are well resolved. I think if you show it to anybody, they'll say, oh, yes, of course I have two dimensions. That's exactly what we have been doing for several years. And we connect the dots and do our structure, do our computations, whatever we want to do. So that's potentially a way out. So now I'm going to redefine this definition of a multiplet in a group of vectors. Multiplet is a group of vectors that precess in unison around its chemical shift vector. We understood that in one of the earlier slide. I'm just going to modify that a little bit. I'm saying a multiplet is a group of vectors that precess in unison around a chemical shift. It can be an acquired or evolution, a quote-unquote correlated time domain. As long as I can sort the multiplet around one of the two dimensions, I'm cool. I sort it. Once I have that, then I can do whatever I want. I'm still in the baby step. I come back to the same tiny little challenge. I need to do this. I think I have a way to do this. I still need to do it automatically and objectively. That's a challenge. So let's take a look at azithromycin 2D spectrum. What would I have do with the 2D spectrum? I have this 1D, I have this 2D. If I have a carbon, I put the carbon on the vertical side and then I connect the dots. Alternatively, in the problem that I'm facing, I want to somehow make this proton spectrum homonuclear decouple itself, or I want chemical shift spectrum. So I look at the projection. That's obviously is completely not very useful for me. It's significantly overlapped in the projection. Most of the time, it's a nice little thing to show, but most of the time, it's not that useful. I look at traces. I can do this automatically. Yeah, I can do a peak picking. I say, okay, at these peaks, show me a trace. It shows reasonably fine, but that's not what I want fundamentally, because I really want a sum projection of these peaks. I don't want a trace. I want a sum projection of every individual cross peak in there. That represents a proton in this dimension and that carbon in that dimension. So I want to resolve some projection, not traces. Why? Here is another example of why we need some projection, not traces. This is a spectrum of ubiquitin, right? And the moment you see this in the azithromycin, it was too easy. The moment I look at ubiquitin, I scratch my head. I don't even know what structures of these things are. I just scratch my head and I have too many dots in there. I want to resolve it better. I want a cross-peak resolution better to the level of this kind of a red dots in there. Yeah, I don't want to do peak picking. Then that becomes another step for me. I just want higher resolution in there. How do I get higher resolution? So I can generate, quote unquote, generate projections of, let's say, these 4 peaks there. Yeah, individual, independent of each other. Yeah, I want to have that. I want it all. So better cross-peak resolution. When I say better cross-peak resolution, the very moment I say that to a spectroscopist, including me, 15 years ago, I'll say, go collect more increments. Increase your T1 max, increase your T2 max as much as you can, as much as your probe can take it. That increase me higher resolution. That's what I want to do. That's exactly I don't want to do. Because the point is, I don't want to spend my time. I don't want to spend my time in running experiments for very simple reason. I don't have a spectrometer. I sit in my home office. I don't have a spectrometer. I don't want to do anything pulse sequence. I did a living with pulse sequences. I don't want to write any pulse sequences. I don't want to write. I don't want to collect more data. So I want it at a minimal cost. Somebody gives me FID. I want to be able to get the best resolution there can be out of that. Can we do that? So let's take a look at truncated FID. That's the first challenge that we need to face. We do live with truncated 2Ds. That's more often than not, that is a routine data collection. Truncated T1 max. What does that really mean? So I went back again. I started taking baby steps. I went back to my prednisone example and say, okay, here is my prednisone example. How does truncated FID challenges me in this one particular problem? How does truncated FID changes, or how much do I need to give up resolution? That's the fundamental question. How much do I need to give up resolution? Is there a balance? What is the balance in there? Okay, so here is the, I'm going to now go faster in our process. That is, here is my FID spectrum. I take that FID, put it into my craft machine, we generate a craft table, and then I sort it. I sorted it. Yes, because it's a baby step. I know what I'm looking for. I'm going to see if I can do that. So here is a sorted, that quartet, a doublet of a doublet. There is a sorted. Just to alert you, the workflow or the data flow is from there to here is a craft with the sorting. And then once I have that, I can simulate all these guys from the table. I can calculate CRAFTps from the table and all that. As far as CFT is concerned, I just take that zero fillet if I want, squared cosine, window, and Fourier transform, or whatever, right? So that's what I want to use. That is an example I want to use to evaluate how low can I go in my T1 max and T2 max without giving up resolution. Right, that's a fundamental, because my challenge is to get the good resolution so that I can do a good projection. That's fundamentally what it is. So I just want to understand this. How low can I go? Here is the same sample run 1/4 of the acquisition time. So my T1 max, my T max in there, this is a 1D. Yeah, my T max in there is 445 milliseconds, which is 1/4 of the original data that I was collecting. So I'm just collecting only 445, 1/4 of the data, truncated, right? Obviously, you can see this zero fill, square sine well window function. You get a broader peak, but the same FID, the same craft table from this FID. If I sort it, I get this four models. Bayesian comes back and say, you have four models. You have four models in there. These four models have frequency, decay rate constant, phase, and amplitude. And then I can simulate, I get this. If I look at this and look at that, and say, voila, I have a spectrum which I can't differentiate from this model. Even though, yes, is that a question? Okay. So even though I use only half, 1/4 of the increment, I get the same spectrum. You can see the line, even the line width at the half height is 1.5, and it's pretty close to, within experimental error, pretty close to that, within computational error rather. I can push it down. Now it is 118 milliseconds, even further out, right? This is a typical T2 max. Typical 100 to 150 millisecond is a typical T2 max in a T2, in a 2D. If I go there, if I take the same thing, if I just do a Fourier transform method, I have to use a cosine. I will show you a picture without, if you don't use some kind of a window function, how the spectrum will look like. But that's beside the point. But if I do the same through, yes, I don't have enough length of the acquisition time to resolve that tiny doubler, but I can generate two averaged out two signals, and if I take a pure shift out of that, out of these models, I still get a 2 hertz line width. Line width is fundamentally, I don't think I have that here, unfortunately, but there is a slide that's coming down the pike. So I can go down. So this is not, in other words, T1 max and T2, or T2 max at least from this particular case. T2 max being short or truncated is not a serious issue. I'm willing to live with that 2 hertz line width if I can, and if I can solve this. So, okay, what about cross peak resolution? I can definitely do T2. I'm willing to live with that, or it's close to what what I typically collect, which is 100 to 150 milliseconds. What about T1 max? Yeah, that's a FT2D. That's your individual traces in that FT2D, some region expanded. That's your cross peaks in that FT2D. Line width is dominated by zero fill and operization, not by decay rate constant. So when you change the line width, increase or decrease, it affects both sensitivity, which is the signal height to noise ratio, and resolution, ability to resolve two neighboring signals. Line width is a very critical parameter that we want to be careful about. The moment this is a 64 increment, if I may, HSQC, and I am not happy that it is too broad. I would like to have it better. What do we mean by line width at the half height is affected because of zero filling operization? Which one? If I don't operize, these are a series of simulated singlets. It's a series of acquisitions, 1.82 second Tmax to 14 millisecond Tmax. If I just do an FT after zero fill, that's your peak height. That's your line width. That's the best you can do. Just a FT. So what we do, we have this serious sync function, sync wiggles, what we call sync wiggles, or Fourier transform wiggles, zero filling Fourier transform wiggles, truncation artifact, whatever name you want to call it. You have this, so we end up having to put some kind of an operization. In this case, when I did a Gaussian window, if you do that, then everybody is happy in terms of visualization of that FID. That's what we typically have been doing when we have a 64 increment and the peak is broad. We go back to the lab and run 128 increment. We go back to the lab and then set 64 increment, but do it non-uniformly sample, do a 50% sampling density, and give me equivalent to T1 max of 128. I doubled my resolution. I doubled my line width, whatever you want to call it. But guess what? We are dealing in this area of loss in signal to noise. We go there and buy $100,000 probe that gives you 2,000 to 1 synchronous on ethyl benzene, come back and do an HSQC and shoot ourselves in our foot. Because we need to deal with this. We have been living with this for a long time. For a long time. I put a number on these. This is the sensitivity loss that we have had. If I do 250, nothing else has been done other than I just collected only the front end of the FID. So why should that affect the sensitivity? Because if sensitivity is equivalent to what we call detectability, that's the first point of the FID. That's always there. Yeah. So whereas in craft, we don't need oxidization. We can do whatever we want without any oxidization. Oxidization is just an example. So let's take a look at the results. This is published already, so I'm not going to focus on that. So here is the FT, that is a craft along F1, and that's the same vertical scaling factor and all that stuff. That's your craft F1. Let's look at it from the quote-unquote sensitivity, right? Doesn't matter. 28 millisecond acquisition. This data is simulated from a 28 millisecond FID. I get 99%, except instead of simulating 28 millisecond, I say simulate to 32K. It's a cost of computation. Doesn't take me more than one more second. Just like an FT, make fed, done. So I haven't lost sensitivity. I haven't lost resolution. These peaks are pretty strong. So yeah, I am willing to give up some amount of line width differences in there, computational errors in there, and all that stuff. So that 78% of the total sensitivity I can get on the resolution that I get without costing me anything. Without costing me anything. So I'm going to skip this because I'm coming short on time. I have a lot of things to talk about. This is a doublet instead of a singlet, and we will talk about that. So the craft F1 workflow goes like this. This is an FT workflow. So you take FID, you do a F2 transform, you generate an interferogram, you do an F1 transform, you get FT2D. Everybody does this. All of us are doing this. What we are going to bypass is we are going to take this guy for every F2 position in this interferogram. I'm just going to send it through the Bayesian pipeline. And then Bayesian says, that particular trace did not, this is an FID. That's a 64-point FID. Yeah. It says that, in that F2, there's no signal. There's no model I can find. Or I can find one model, or I can find more models. It's just the number of models that's in there. Completely objectively, it says it gives me a table. I have the same number of tables as the same number of points along the F2. It's a huge, humongous table, except it's sorted out in F2 frequencies. Yeah. And then I'm going to come back to the X table, class peak table. I'm not going to talk about that at this point. 2 slides down, we will zoom into that. Essentially, I can take this thing. This one doesn't have any information about whether that came from a 64 increment interferogram. So I need to simulate only 64. I can simulate as long as I want. So I simply say, take this table, reconstruct my interferogram, but this time, take it up to 1K, take it up to 2K in that dimension. All I need to do in FT, and you get an F1 spectrum, which is high resolution. Nothing was done other than just pass it through the table. And that it's equivalent to a super linear prediction, except it's being linear predicted at a model level. At every model in this bunch of tables, I'm saying just linear predicted. It's not linear prediction, it's just a mathematical operation of how many points you want to simulate, you want to calculate, and that's about it. It's not even a function. It's a function already exists in there. I'm not even fitting into a coefficient. So that's it. So bottom line is the cross peak is resolved in either. If the cross peak is resolved in either acquisition or evolution dimension, it doesn't have to be necessarily both. you can distinguish and describe a cross peak. And in FT, zero fill, oxidized FT, excellent looking 2D spectrum falls behind what you can do simply by going through a tabular domain. That's it. Yes, you do always have a question of Bayesian. I'm just going to defer you to previous work already done. But it is what we can do with tabular domain. I'm focusing on what can we do with tabular domain. That's what you can do with the tabular domain. So I get a better cross-peak resolution. So here is a workflow. Let's focus upon this part of it, because we really want is a better cross-peak resolution. I want that automatically, and I want that to generate a resolved sum projection. Fundamentally, that's what I wanted. That's my challenges I described to myself. This is eventually the ultimate goal. This is my first step in the problem. Because of this, I need to improve this. That's already there, and it has to be automatic, and we'll look at that in a minute. And I want to get that. If I can get that, I got that, and without giving up any cost. Okay, and we already challenged ourselves on the truncation artifact, truncation effect. That's a no effect, well, minimum effect, if you may. So let's zoom in onto that particular step. This is the most critical step in the entire workflow here. So we want to go from craft F1 to sorted F2 spectra overflow, meaning we want to take it from this to resolved sum projections at each proton automatically. So that's the next challenge we are facing. What we want, what we have in our handle is the computational error, computational uncertainty, if you may. So that is an automatic output of any computation. You are defining a property and you have an error in that property. That is your average. So in this case, you have defining a property, frequency property, F1 frequency property of hundreds of models in these tables. And we essentially take the statistics of average of this. I'm a conservative, so not in politics, but in conservative, but I want to conservatively take 75th percentile error. I take the average plus 2 sigma and add that, make that as 16 hertz. So the fundamental point is, within 16 hertz, I can't tell. I can't tell whether it is an independent cross-peak or belong to a set of cross-peak. I am perfectly willing to work with 16 hertz of uncertainty, because we just saw how much we lost just because we oxidize and Fourier transform, which we don't have to do that here. So if a cross peak, so we made a definition, a cross peak from this group of table is a group of F1 models that are within the F1 estimation uncertainty. I take that 95th percentile. And then he said, and it also have to be in contiguous F2 traces, all our multiplets. I'm exploiting the first step in this entire workflow, which is a Fourier transform along F2. Yeah, Fourier transform along F2 to generate the interferogram includes an oxidization. That gives me the overlapping region that I'm going to exploit. It has to be in contiguous F2 traces. I use this rule. If I use that rule, I just go back with this rule. I go back to this table, the huge table that has there is a table for every F2 point. So if you have 1,000, your Fourier number on that dimension is 1,000. There are 1,000 tables there, or 2,000. There are 1,000 real tables there, real component tables there. So we just go back to the table and say, this is the rule. Just sort it out. So here is one sorted out P. It says there is a group of offset. Just focus on this blue line, blue section. There's a group of offsets that are within the 16 hertz and within this trace index, within the contiguous trace index. So it says, okay, that's a cross peak. That's a cross peak within this acquisition of this 2D, which happens to be HSQC, which happens to be run with 64 increment, which happens to be run with 1.1 150 millisecond acquisition. So whatever your input is, with that input, this is a set of models that belongs together. Or you can say this is a set of models I can't resolve within the uncertainty that I have. When I have that, then I can take that set of models and say, that's a cross peak, that's a tag, if you may, that's the weighted average of the F1 chemical shift from these models. And then this is my F2 trace. I generate a cross peak. Essentially, that cross peak is not really a line. It is a draw in a chest of drawers. You open that drawer, you get these. So that's a three-dimensional table. This cross peak table is not two-dimensional, it's three-dimensional. The third dimension being each one of them having the independent F1 chemical, F1 offset, amplitude, decay rate, constant phase coming from that F1 tables. So once I have the draw, there's nothing stopping me from continuing that. So I keep doing this over and over and again until I'm exhausted with all the models that are in there. I generate a cross peak table. This is not coming from peak picking of a 2D spectrum. It came from grouping them already in there automatically using two constraints, F1 constraint, F2 constraint. Once I have that, that peak essentially represents that two-dimensional table, which is a table along the plane of the paper, yeah, represents this cross peak. I can do that for everybody. What about your question? One might question, what about something like this? There are two cross peaks that has the same F1 chemical shift. That's a methylene, obviously. That violated this rule. So they belong in two different drawers of your cabinet. What about in here? There are overlapping. You said contiguous F2 traces. There are contiguous F2 traces that has two different F1 cross peaks. That violated the 95th percentile rule that we supply. We simply use statistical numbers to say that's what it is. This one is our introduction of exploiting the aquatization that we did along the F2 dimension, which we were doing that in order to generate a decent interferogram anyway. So that's already that sorting is trivial because of this rule. The sorting of these four, even though they are overlapping in here, and this sorting of these two, even though they are overlapping in here, is trivial. So that's it's trivial because of this rule, because of that rule up there. Yeah. So the moment I have that, I can essentially take this table. Remember that table that I showed you is two-dimensional. That is a draw. It's a draw full of models. That draw full of models has two specific information. That is, it belongs to a F1 ppm with offset range and F2 trace indices that are adjacent to each other. That's all the only models in the draw. I can generate a 2D spectrum out of that. I can generate an interferogram out of that. I can generate a projection out of that. Because I don't need to project, I don't need to know where it is. I just simply project the entire FID, entire spectrum along F2. That's my F1, F2 projection of that cross peak, period. There's no uncertainty in there because that uncertainty is all dealt with in sorting that into tables, into drawers of your cabinet, if you may. I can essentially, so now if you think about it, I haven't done anything in between manually. I started off with interferogram. I ended up with F1 selective 2D spectrum without manual intervention, other than using whatever is the input values generate, the uncertainty, the contiguous nature of the F2, and all that. It's all automatically done by the input FID, not user input. Just the rule is user input. You can violate that. That's absolutely fine. So that is automatic. I can do this for every draw. So essentially, I just generate one 2D after the other, one 2D after the other from each draw in that X-peak table, each draw in that cabinet of X-peak table. And essentially, I get a singular cross-peak 2D spectrum. I simply project that, and I get an F2 spectrum a F2 spectrum at every F1 chemical shift from going from that interferogram straight to this table, straight to this. That's my, essentially that interferogram leads to this. Fully sorted. It's not a projection along the F2 dimension. It is slice projection at every individual F1 chemical shift. Once I do that, how does it automatically done? Watch, remember this? I simply took this, I simply took the output of the uncertainty in there, I applied that to the table, and I generated that. So now that is all automatically done. And so this entire generation of F1 selected F2 spectrum, I don't want to call it a trace, I don't want to call it a projection, it's a spectrum. It's an F2 spectrum of a single crosspeak in each trace. Essentially, we simply sort of took out all these, addressed all of this, and I have the sum projection. What do I do with that is the question. That's the easiest downhill. So I have spectrum. Somebody long time back told me in FT and inverse FT are equivalent, so you are reversible, da da da. So I said, okay, I will take the spectrum and do an inverse FT, generate a FID for each one of them. Except if you don't want to forget that originally we started off with an upwardized F2 dimension. That interferograms are based upon starting from a truncated FID, and in order to deal with my artifact, the sync artifact, and I have to upwardize, and I have to do a project. I have to construct an interferogram. That's where I am starting off with. So that upwardization effect is embedded in that FID. But just like Fourier transform is reversible, weighting function is reversible. If I know what weighting function I reverse that. I multiply the other way, and then now I remove that upwardization function. Because I multiplied by an upwardization function, now I take a division, if you may, multiply by inverse of that, inverse FT, inverse WT. And then it's a single group of vectors that precess around that F1 frequency, single group of F2 vectors precess around that its correlated F1 chemical shift. I don't have to even think, are there other crosspeak contaminated in there, because anything that contaminated is only what I cannot resolve in this entire 2D. What I cannot resolve both in F1 and in F2, meaning your correlation experiment that you use is not good enough. Without that I can simply do a CRAFTf2 and project them all into pure shift, into a single model. So now I can describe that into a single model. This is each one. Imagine that this is each one of them having multiplet model. That's a doublet there. You can see a triplet right there. You can see another triplet type of component right there. There's another triplet type of component there. All of that, each one of them, go through this process. It's a trivial step from craft point of view, and we just generate a pure shift spectrum. So pure shift workflow goes through this. We take it from there. This is all in the conventional domain. We do a CRAFTm to F1, sort the table. I deliberately here, I had this interesting idea of putting this as actually a cabinet. It's not a table, flat table like this. It is just a cabinet of models, draws of models, and then I generate F1 selected F2 sum projection, and I do this. And now I took that draw of cabinet and put it in the face. Now this is, every number here is coming from the craft. There is no logic, there's no rule that I applied other than what was applied in here. It's just simply these two numbers come from CRAFTf2. These four numbers came from CRAFTf1, and because we started with with a real component of the interferogram, we have F2 phase equals 0. So pretty much there is nothing that I did here that I needed to intervene. And I also said, even though I started with an HSQC, I didn't say anything about carbon here. I said F1 and F2. So any homonuclear or heteronuclear 2D input can go through this process. It is not dependent, it is not only for heteronuclear 2D correlations, it's for a homonuclear 2D correlation. Before I show you a quick example, which will be take only 5 minutes or so, I want to put this record straight about what it is and what it is not. I have been talking with a lot of people, and there's a lot of these questions come up, and then I have to explain, no, that is not that, no, that is it. So here I'm just going to summarize some of those. What is it? What it is not. What it is not is very important because we don't want to overrepresent this method. It is not a J decoupling method to do pure shell. It's not J decoupling method. We don't even write a pulse sequence. We don't even go into the pulse sequence. Whatever we start off with, and it is dependent upon only that. It's not even a J measurement method. So I don't know if it is an 8 hertz J or 2 hertz J or I don't even know. It might know if I dig it down, but I don't know in this method. I don't want to see anything. I just want to click the button, put a black box in there, click the button. So that follows that rule of workflow. Essentially it is a singular vector, one for each cross peak, and each one of those vectors is represented by 7 NMR parameters. 2 frequency, which is 2 rate of change of phase in 2 different dimensions, 2 line width, meaning 2 rate of change of amplitude in 2 different time dimensions, and 2 phases, the direction of the vectors in 2 different dimensions, and 1 amplitude. That's it. NMR properties, nothing more, nothing less. That's what it represents. That's what we are hoping to represent. That's what it represents. No more. How good it is, how good bad it is a different question. That's what it represents. No more than that. It is processing in correlated time space, 2 time space. So it depends upon what correlation you are doing. And these are grouped with this rule. There is a rule that we apply. That's also a rule that you can violate if you want. For example, if you want to live with less conservative, more, pardon my pun, liberal, use F delta F1, which is you simply say that, well, I'm willing to live with within the uncertainty of the average uncertainty, not necessarily the 95th or the 68th percentile. Completely up to you. You don't need to even go back and redo anything. Just go back to the table and say, group it that way. So there is a way that you can override that, or user can override it. So there is some room to do this. Contiguous F2 is not necessarily, most of the time, that's a challenge we actually face that we don't resolve because we are working with truncated fits and all that. But there are scenarios where you can imagine that. Let's say you have a third nucleus that coupled at F19. Coupling is 150 hertz. So that's on one of the dimensions, whatever that is. Right? If you have F19, which is the third nucleus, that is passive nucleus, that is coupling, and it's not in contiguous, so it gives you 2 cross peaks. And you can come in and then say, okay, just like you would say, I want to integrate these 2 together, or I want to integrate this and integrate that and add them together to generate my QNMR, you can simply say, I have 2 cross peaks in there, draw a box around it, and then say, yeah, make that into your rule. That's a rule only applied only to those 2 draws in your cabinet. So you are essentially saying those 2 drawers in your cabinet should be together because I say so. Because you, as a chemist, say so. So there is some room to override even that one rule that we apply. And obviously this is all, and I put in for the fun of it. I put in this follows the GIGO principle. Yeah, and then if that's a limit, it's all the same. This is all recorded so you can come back and read this. I'm running out of time. I want to talk a little bit about displays. Here is the 2D craft pure shift 2D craft table. This is a not a cabinet. It is a wall of two dimensions and two dimensions only. Rows and columns. That's it. I can generate a 2D. I can generate those projections. I can just take these 4 columns of this table, generate an inept type of result. That's a 1 second simulation. I can generate F2 spectrum. I can take these 4 columns, which is F2 columns, and then I can generate a spectrum. That's also 1 second instead of all of that. That's all, because everyone is a singular model. Everyone represents a singular cross-peak. What about in a highly crowded region? Here is an example. This is published in analytical chemistry. This is an example of cyclospore in the upfield region. Now that's different regions. Overlap. That red line is all FT result. Contours, projections, data. The blue lines are CRAFTps, pure shift. I have to keep the FT results 40 times blown up in vertical scale in order to keep it in scale. With the CRAFTps. Alternatively, if I plot them together, CRAFTps will be shooting out of the page. You can generate not just inept 1D type of experiments. If it is F1 is not equal to F2, or if it is a C13 spectrum, or you can also do F1 selected, F2 spectrum, each one of them being a pure shift, because it's a singular model. It's not pure shift. It's a pure shift, not chemical shift, not necessarily chemical shift. Most of the time it is, but not necessarily chemical shift, because it's a cross peak. And the other way, I can do an F2, at every F2 chemical shift, I can generate, in this case, carbon spectrum. High resolution. These are all 1 second, 2 second from the same table that came from the same data. And even a pure shift HSQC, the pure shift, conventional pure shift pulse sequence. Remember, we have 2 places we can manipulate the table. One, but actually doing the pulse sequence differently. Fantastic. I did a living out of it for 20 years, 25 years. We can do that. But we can also do that. It's not one or the other. We can do that. So here is a pure shift HSQC process conventional way, process with CRAFTps. Watch all these doublets which are on the geminal coupling is not which is that we understand all of that. If not, you go to Manchester's fantastic website. You can explain. There's a good explanation for all of these pure shift methodology. My source for understanding many of these. Here, that's all singular. Everybody is a singular, except this guy, which is actually 2 AB spin system. Actually, that is a methylene. Actually, that is a geminal coupling. Actually, that is a very strong geminal coupling. That shows up. That is also a singular. It's a singular. That's those 2 methylines from within the acquisition point of view. That it says, I can only fit that into a singular model within this rule. Except that look at these numbers. These are all all the pure shift are projections and 2Ds are plotted. If you have a vertical scale of 1, these are all plotted. Projections are plotted 12 times bigger. 2Ds are plotted 5 times bigger. So that's in order to keep it all in the same scale. That's pretty much what it is. This is one of my most favorite experiments. We did with Gary Martin's group. We did a lot of variations of HMBC in the good old days. It's an HMBC spectrum. F2 is a display apodization, varies with pulse sequence flavor. This is your cross peaks. Your cross peak F1 is chemical shift, all homonuclear coupling constants in there. Chemical shift of F2, which is this, all homonuclear coupling constants, couplings, all heteronuclear couplings, because we don't typically do decoupling. Even if you do, then you have the other one. So F1 is absorptive, maybe not, depending upon how you process. F2, maybe it's a pure shift, it's a phase sensitive or acquisition, or you had a gradient. You didn't bother with the novel sequences. So it depends upon the flavor. This is all. What does that all mean? It all means that cross-peak is poorly resolved within the cross-peak itself. They are all broadened by the un the J coupling that are not removed. J coupling, hetero, homo, in phase, anti-phase, any of that. It's not removed. So that shows up in your in your traces and projections and whatnot in either dimension. You do CRAFTps, you get a carbon chemical shift and a proton chemical shift. That is your craft pure shift spectrum, phase sensitive in both modes. I'm using Gaussian because I don't have the patience to wait for a 32K by 32K transform. So I just say, okay, just transform it shorter. So I use the Gaussian finisher, but you don't need to. If you have a very good computer, there is your inept experiment, inept type of carbon spectrum. It's not inept here, but carbon spectrum at each proton chemical shift at the resolution similar to, at the resolution and line width similar to carbon. Pure shift, proton. 2D of cozy. Yeah, sure. Why not? Why not? That's a 2D double quantum filter cozy. You can apply that. That's perfectly valid. Perfectly valid in there. And here is traces. I'm going a little faster because I'm running out of time. Toxi, this is my favorite. Here is a 2D spectrum of the Kraft pure shift 2D spectrum. Very interestingly, you can do certain things with the table because it's a table. Because remember, in the table, you can change your representation. How the frequency domain look like by doing some kind of a sorting. What's one of the most annoying thing? Annoying thing in a homonuclear 2D is the diagonals. Even in a pure shift spectrum, that's a diagonal. Invariably in my, if I work with a very small mixing time, it's too big. So I can sort it out. I can simply go back to the table and say, make a rule that here is a table. Take anything that has F1 equals F2, put it away. Anything that's F1 equals not equals, put it away. One is diagonal, another one is half diagonal. I generate a diagonal 2D, I generate a half diagonal 2D. I can project it without the diagonal in place, or even better, I can go back and say, I like diagonal, but I don't want it big. You can simply say, go to the diagonal 2D table, make only 20%. Put only 20% of that amplitude in the final 2D. So this is diagonals attenuated 20% to 20% or 80% attenuation. Diagonal attenuation, attenuated 2D. So you have the benefit of having the diagonal as a register in your analysis. At the same time, it is not very big, annoying you. That becomes very important in noisy type of experiments as well. Here is another interesting way you can do table. It's a table. Yeah, I can simply say, I want to generate a 2D representation, essentially 2D FID. Behaves Fourier transform FT2D on that CRAFTps FID, simulated FID. That will give you a toxic cross peaks in one half, meaning when F1 is less than F2 or whatever, the other half, other triangle can be noisy. And this comes from two CRAFTps table, just merge them in a particular rule. Now you have a methodology with which you have this table. How am I going to visualize? This is a very useful type of representation where you can just put your cross-peak, put your cursor in there and generate traces and analyze. Those are my diagonals, and anything on this side is noisy, anything on the right side is toxic, and so on, so on. This is all just display. I wanted to go back and show you the ubiquitin. The red dots I showed you is actually CRAFTps from the same data, same 15-minute data. And these are your N15 edited or N15 sliced proton pure shift. Needless to say, that's N15 pure shift. but this is at every individual N15. Think of this 25 to 1 vertical scaling factor in order to keep them in place. Now, if there are more examples, I'm going to skip all that. H2BC, cigar, 1 adequate. There are some in the supplementary material. We can talk about it. I want to just take 5 minutes. I know I have taken a lot of time. I want to take 5 minutes to what next? What can we do with this other than, oh, nice looking spectrum? What else can we do? This is 100 megahertz HSQC on a quinine non-analysis data. That is your FT2D. That's a total experiment time was 20 minutes. I think there's a 40 increments, 20 minutes acquisition. Probably loaded sample, doesn't matter. So that's a pure shift spectrum. Yeah. Not the pure shift, not the HSFT, not these phases. Look at this spectrum. This is the carbon simulation. I go back to the table and then take only the F1 information from there. F1 chemical frequency, amplitude, decay rate, constant phase. Those are the only parameters. I take only those from the table, F1, and simulate that. That is an inept type of spectrum. Carbon inept 1D, inept indirectly detected inept spectrum. And that's actually noise, vertical scale, blown up noise. Either a multiplicity editor, not multiplicity editor, it's all in the table. You can say, I ignore my phase. You can say, retain my phase. That's a rule, NMR rule. That's what we do. We want to flip it up, flip it down, or change the color. That's what we do. That's the same rule. It's take into account or don't take into account. It's rule. But that is the kind of signal to noise of an inept resolution signal noise. These are very sharp resonances, 2 hertz, 3 hertz typically of carbon in benchtop at 20 minutes acquisition. That's with that kind of a sensitivity to burn. That's dot number 1. Let's look at a different dot. This is an ASAP HMQC. It's probably an old data, very old data from our library. 1.5 minute acquisition is Taxol, okay, 10 millimolar Taxol. And that is my ASAP inept, I indirectly detected ASAP inept from the same data. That is a vertical scaling factor of the noise. That's my signal. That's my spectrum, simulator spectrum. And this noise is in there. I'll show you in a minute. So that's the spectrum. That's a 1 second T max of that simulation. Here is my vertical scale to show you that noise. That's the resolution. These two cross peaks in this particular place is 5.6 hertz. All of this with 1.5 minute of acquisition on a conventional 20-year-old probe and hardware, probably on a 10 millimolar Taxol in the good old days. 1.5 minutes, that's the carbon spectrum. Now that's a dot number 2. What about ASAP HMQC on a benchtop? Why not? Why not? That's a question I want to ask. Why not? I think that's possible. This is another representation. It's all because we have not been looking at it from an intermediate domain, which is tabular domain. How do we measure and compare signal noise? This is an important point. I'm just 1 slide or 2 slides and I'm done. So noise fundamentally is a measure of uncertainty in the input fit data points. So it's a 1D, it's a number of points you have. You have 32,000 points in a regular 1D or 64K points in a regular 1D. Each data point has an uncertainty in the measurement. So that's what you generate as a noise. In a 2D, it is NP times 2 times number of increments. We all understand that. That's fine. That's the measure of, that is the uncertainty. That's the measure of noise in the spectrum. In the spectrum too. I can simulate, which is a simulation, obviously no noise, but I know I can measure the noise level in the spectrum and I say, okay, go back and muck with every one of the data point that's in there in the 1D 32,000, 64,000, simulated. So there is no uncertainty here, simulated. And then we say, okay, at each one of them, insert this noise in there. And then we can transform that. This is a simulated fit, but I added the same amount of noise that I measure from the spectrum. And I add the same noise in there. Now I can compare the sensitivity differences. The sensitivity improvement, whatever it is, with respect to a constant noise. With respect to a constant. That constant noise is a measure of the uncertainty in the input FID. Yeah. So in a 2D, it's FT2D, that input is 171,000 data points. Uncertainty. I can measure the entire thing. I can measure the whole spectrum. I can measure what is my noise floor. I can go back to the simulated pure shift data, which is 10 million data points, and then say randomly change the amplitude of each one of those 10 million data points so that the RMS will be exactly the same as the RMS that was in the input FID. And that's the same thing. Now I can compare these two. I can compare these two with noise being my constant, random noise being constant, oxymoronic statement. Here is the spectrum. That's a projection of FT result, projection of the pure shift results that has noise in there. We added that noise. That's the different F1 projection, F2 projection, this is F1 projection, different traces. And we just blew both of them vertical scale up. And this tells you how much of a signal to noise, our conventional methodology of signal to noise increased versus with respect to a constant floor noise. That can be analyzed, and then we say, we generate 60 times signal to noise as per the definition. Signal to noise is signal height to noise height. Nothing more. We are not saying anything beyond that. But we are going to say something beyond that very soon. Sensitivity, we have been equating that to the detectability. This is what I can see, so that's my detectability. That's our definition of sensitivity, detectability. Let me show you what we are working on. And this is we are working with Ron. We are not talking yet. We still work in progress. This is an HSQC of Ron's favorite sample, 1 milligram brucine, and he told me that that's actually 4.2 millimolar brucine HSQC. Yeah, that's an HSQC. He can probably tell you all the details of how he collected the data, what hardware, and all that stuff. That's beyond my scope of even patience of listening. But let's take a look at the C11 proton, which is this. That's the most insensitive cross peak spectrum in the FT result. Meaning that I just did a line list of picking of my 2D and then say, which one is the smallest one? I said, okay, I'm going to focus on that. So that is the best sensitivity trace that I can pick out of that spectrum, FT2D spectrum. Yeah, measured RMS noise is already put in there. And then what we said was, we haven't done the experiment yet. We did a mathematical or noise titration experiment. So we titrated noise in and scaled the FID down, equivalent to 6 times lower concentration. So this is a 700 micromolar brucine. The same trace, signal to noise is 2.7, makes sense. That's 18, 6 times 3, fair enough. Yeah, your signal to noise is, your signal is directly related to your concentration. So it's about 6 times lower signal. Noise being the same, because we have the same noise, meaning that if I had collected a 700 micromolar brucine spectrum under exactly the same condition, we can safely assume the noise, which is the uncertainty in every data point that is being collected, is similar in both cases. In the 4.2 millimolar spectrum and the 700 micromolar spectrum. Noise is a constant. You can see that we took that approach that we need to be proven that yet, but the RMS noise is a constant because we did this. So that's the peak you're looking for. So from a sensitivity point of view, from a detectability point of view, that peak is within the 3 times RMS rule that we typically use. 3 times RMS rule is in a normal distribution of statistics. 3 times is 99.9% or 99.5% confidence level that it is not a noisy peak to peak noise. It's not a random noise. It's actually a signal. 99.5% confidence level is 3 sigma over RMS. Yeah, that's the rule. It is less than that. So ideally, unless you are gung ho about it, you would take this with a pinch of salt. Ideally, because that is also about the same. This peak that's right here is also about the same. But that's actually a noise. So you can do this. Now, the same thing. I process it differently. Detectability is not same as signal to noise. Even though I'm using signal to noise, detectability is the processing method that you are using. Detect more or less. Not because it is taller or shorter, but because it detects. And we need to come up with a way to differentiate it. Do I have an answer? No. Hopefully, we will have discussion about it at the Ivan ENC conference. I'm planning to talk about this. I don't have an answer, but definitely signal to noise is not a detectability. That is a 204 to 1 signal to noise, but it is the same sample I'm able to detect. So what is the definition of detectability? It is a bigger discussion. I don't know the answer, but it's a work in progress. With that, I'm going to stop. Sorry, it took a long time. Anybody has a question? If you have a question, burning question, or critique, feel free to. I'm shielded up.
Okay, thanks.
Thank you, everyone.
Okay, bye.